Welcome to NVIDIA's modern CUDA C++ programming class. In this first video, you will learn how to program on the GPU using NVIDIA's latest programming tools. This video is part of a broader video series teaching CUDA programming. In the second video, you will learn how to unlock the GPU's full potential by using asynchrony and CUDA streams. In the third and last video, you will learn how to implement new algorithms on the GPU using CUDA kernels. Links to other videos can be found in the description. While watching this class, you will regularly need to pause the video to complete exercises. There are two platforms where you can complete those exercises. One, on the Accelerated Computing Hub. There, you have access to all the slides and notebooks containing the exercises. It's open source, free, and can be run locally if you have a GPU or on Google Colab. Two, on the GLI platform. The content is not free, but you will be given access to a GPU, the final assignment, and, after completing the class, to a certificate. Both links can be found in the description. To go on the GLI platform, click on the link provided in the description, go in the GPU hands-on section, and click on the Start button. Eventually, a GPU instance will be given to you. When the instance is ready, you will be given access to all the content and all the exercises. So now let's start. So this first section is just to see how you can accelerate applications using GPUs in the easiest way possible. So first, we'll learn about execution space and how they can allow us to achieve huge speedup just by doing simple code changes. Then we'll talk about how we can extend those algorithms using fancy iterators. We'll then talk about a few vocabulary types that you can understand better what we talk about here and there when talking about CUDA and parallel algorithm. Then we'll learn more about parallelism itself, and especially in GPUs, and how we can achieve those 100x speedups. And finally, we'll talk about the notion of memory spaces and how they can also end up accelerating your code by up to 100x. So let's first try and understand what's the difference between a CPU and a GPU. So let's consider a bus and a car. And the question could be, what's faster between a bus and a car? Well, this question doesn't really make any sense if you just take it like that. A bus, it will take longer to move a few people because usually a bus is slower than a car. But a bus can take many people, hundreds of people, if the bus is big enough. While a car, surely it can go usually faster than a bus, but it can take only a few people, maybe 5 at the maximum. So which one is faster doesn't make really any sense. The question is, what kind of speed do we want? Do we want to just move one or a few people as fast as possible, or do we want to move many, many people as fast as possible? Depending on the answer, the bus or the car is the best solution for you. And that's the exact same thing for a CPU and a GPU. On the left, you have the CPU, and you can see that the latency, so usually the amount of time you need to wait for some piece of data to arrive, is around 100 of a nanosecond. On the other hand, the memory itself, so your RAM, just allows to move 100 gigabytes, around 100 gigabytes per second. This means that you can read or write data very quickly, but you can only read up to so much data, in this case 100 gigabytes per second. So your CPU is your car. It moves very fast, but only a few amount of data per second. On the other end, the GPU is different. The GPU has a higher latency than the CPU. It means it needs more time to move a single piece of data around, usually around 500 nanoseconds. That's 5 times more than the CPU. So the GPU will take more time to take some data, do some modification to it, and then write it back to memory. But on the other side, it has way more bandwidth, way more memory bandwidth. A GPU usually has around 1,000 gigabytes per second, which is one terabyte per second. That's way more than what the CPU can offer, which is just hundreds of gigabytes per second. So the GPU is your bus. It's moving more data around, but slower. But so in the end, if you want to move a lot of data, the GPU will be better. But if you want to move less data but very fast, the CPU will be better. So we might consider what kind of problem can benefit from the GPU bandwidth. So here we have an example of a problem where we have 3 cups, and those cups are at different temperatures, so 42, 24, 50, and we want to simulate how they cool down over time. And so for now, we'll just simplify and say just 1 cup is 1 temperature. We'll not take into consideration all the other things. We'll just consider the temperature of each cup. And so we just have a bunch of cups. They all have a different temperature, and we want to simulate how the object will cool at room temperature. So if you leave your cups after getting them cold or hot in the room, how will their temperature change with time? And so the question might be, for this kind of problem, so if I want to simulate how my cups cool down or heat up with the room, when is the GPU useful? When is the CPU useful? And so the only question you need to think of is, how large is N? So how many cups do you have? So let's say we wrote the code, right, to do this simulation of the cups. And we first tried on a CPU with a single thread, a CPU with all the threads, so 64 threads in our example, and on the GPU. And we try to look how much time it takes. And so if we just have 512 cups to simulate, we see that a CPU with a single thread is extremely faster than a GPU, and even faster than a CPU with 64 threads. That's because usually when you want to use many threads on a CPU, it adds a lot of overhead. The same goes for the GPU. The GPU has some overhead to create the data, move the data around, etc. And there is, again, the GPU has more latency. So with only 512 cups, a single-threaded CPU is more efficient than a multi-threaded CPU and a GPU. Now, if we go further, and if now we have around 64,000 objects, now we see that finally the multi-threaded CPU is faster than the only one-threaded CPU. But the GPU is still too slow. That's because 64K elements is still not a huge amount, considering what the GPU can do. And so if we go further and we go to around 200 million objects, finally, the GPU is 10x faster than what the CPU can do. So now the CPU one thread is the slowest, then we have the CPU multi-thread, and then finally the GPU. Because finally we have enough elements, so here 200 million, to saturate the entire power of the GPU. That's the same with the bus. If you use the bus, but you only have 5 people at a time in the bus, the car will move more people around per minute than the bus. But if you have 200 million people to move, then the bus will move far more people than the car is able to. So now let's look at how we would implement this code. So our goal is to simulate how the cups gradually approach the ambient temperature using the equation shown below. So this is a very simple equation. So you see that at each step, the equation adjusts the object temperature based on the difference between the current temperature and the room temperature. So each object cools down independently. So each object has its own temperature and each temperature evolution. And so they all follow the same rule. And so one object temperature doesn't affect the others. And that's great for GPUs. For GPUs, we want many things to happen in parallel, hundreds of thousands, if not millions. And we also want them to happen independently, preferably. And so here you can see at the top, you can see that the cup starts with 42, 24, and 50 degrees, while the room temperature is at 20. And so if we apply this temperature of previous temperature plus K times the room temperature minus what was the temperature at the previous step, we get the next temperature. And we see that here, 42 goes to 31, 24 to 22, and 50 to 35. So we see that all three, they start converging to the temperature 20 at different rates. And so this is how the code would look like. So we start by defining the cooling coefficient of 20. We define K here to 0.5. We have our 3 cups with our initial temperature of 42, 24, and 50. And then we define what we call the lambda function in C++, and this lambda function is just the formula that we just defined in the previous slide, which is just this ambient temperature minus the current temperature, and we do this times the k, and that's our new temperature. And so once we have defined this lambda function, which just define at each step how the temperature evolves, we can just have our for loop here that will go from step 0 all the way up to step 3. So we'll have 3 steps, step 0, 1, and 2. And each time we print the temperature, how it evolves, and we call the std transform function. So the std transform function is a simplest function from the STL, which applies a specific lambda, specific operator to a whole container. So here we go from the vector TMP, which is our 3 cups, from the beginning to the end, and we just applied our operator, and we do that 3 times. And so we can see on the right that we go from 42 to 31 to 25 for the first one, and so on for the other ones. And so again, we have our multiple objects. They all cool down independently, and they cool down in an iterative manner. And so for now, obviously, this code's run on the CPU because we're just using a std vector and std transform, and we have the 3 steps. So if we take a little deeper look at what std transform is doing, transform is literally transforming the input. So you first passed what the first and last element of your container, here our vector, then where you want to store the results. In our case, we just wanted to store it in the same container, and finally the operation. So here you can see on the right, again, we have our lambda function. We're applying it to the vector on the left. We go from first to last, and each time we just apply the operator, and we store the results in the output vector, which is here in our example, the same as the input vector. And so if we wanted to program std transform ourselves, that would just look like this, right? You just go from index 0 all the way to the end of the vector, and you just apply the operator, right? That's just what std transform is doing. It's going from the start to the end. Could be to a smaller portion, but so here we're going from the beginning to the end, so 0 to the maximum size, and then we just apply the operator, and we store it in the result, which is, again, in our case, just the same vector. And so all of this is happening on the CPU. And so let's first do a quick reminder that CPU, they do not run C++ code. When you write a for loop, the computer is not going to run this for loop. The computer, they do not understand a for loop. What they understand is compile code, binary, CPU instructions. So if you look at the C++ expression on the top, you can see we're doing this temporary temperature plus k times the difference. Well, depending on what architecture you want to run on, the resulting compiler will generate a different instruction. So if we take the first one, so your usual x86 CPU, your Intel AMD CPU, you will use an x86 compiler that will convert the instruction into a VFM-add instruction, which is a fuse multiply add instruction, which does a plus and a multiply at the same time. And so this instruction will work and only work on this x86 CPU. But if you were to compile this C++ expression, this temp I plus k times diff, using an ARM compiler for an ARM CPU, you will get a different instruction. You will get vmla.f32 instruction. Again, if you want to compile this code to run not on the CPU, but on the GPU, then again, you will use another compiler, which is, in our case, the CUDA compiler, and it will again generate yet another instruction, which is fma.rn.f32. And so you can see here that for each different architecture, you will have a different compiler and a different in-the-end instruction that will be executed by the hardware. But at the top, they all see the same code, but this code is not executed exactly the same by the different architecture. It depends on what the compiler will generate as instruction. But so the GPU is not that different from the CPU. In the end, it's just processing instruction, and those instructions, in the end, they do the same thing than the other, but just in a different manner. So this is how it will look like. So if you wanted to compile on an x86, you would just use G++ and specify the output, right? If you were using an ARM CPU, you could use the R64 G++. And if you're running on the GPU, you would be using NVCC. And so if you compile with NVCC, your expression will be converted to executable GPU instruction. But so you might think that just compiling this expression with NVCC will make your code magically work on the GPU. Well, actually, that's not how it works. Because as is, if you just compile your code as the code we saw before using NVCC, your code will work on this. Will work on the CPU. And so that shows that there can be a confusion onto how people think that code can work on the GPU. You need to specify some things in the code to let the compiler know that some part of the code will work on the GPU. So yes, the compiler can convert the above code into GPU instruction, but you need to tell it where is this GPU code. And that's how we will talk about this GPU programming model. So GPUs, they are accelerator rather than just a standalone processor. And so a lot of work like interaction with the networks and file system can only be done by the CPU. If you read from a file or from the network, you will most likely not use the GPU, but use the CPU. So CUDA programmer always starts on the CPU. You will not start a program from the GPU. You will always start from the CPU, just like any C++ program. And so you are responsible as a programmer to explicitly specify which code should run on the GPU. And you should say explicitly, this part of my code should run on the GPU. It will not magically put all of your code on the GPU. You're responsible. So you're responsible to say what code runs where. And that's why we talk about execution space. Execution space is, you say, should my space of execution should be the CPU or the GPU. So at a high level, the execution space are split into two. We have what we call the host, which is the CPU, and we have what we call the device, which is the GPU. And so this should explain why using NVCC alone is inefficient to port the previous code with the STD transform to the GPU. By just compiling with NVCC, you just compile the code, but at no point you said that you wanted any part of your code to be executed on the GPU. So usually, how do we make the code run on the device? So in C++ and in any programming language, in general, we rely on libraries. We do not re-implement everything from scratch, right? If you want to do a sort, usually you will code std sort to do sorting. You will not program your own sort. For CUDA and GPUs in general, that's the exact same thing. Along with the compiler, which is NVCC, CUDA offers a very wide area of GPU accelerated libraries. So some libraries are very specific to a specific domain, like let's say cuDNN for deep learning or cuBLAS for linear algebra. But some libraries that are more generic, and they're just giving you algorithm that will work on the GPU in the same way that they work on the CPU through the standard library. And that's what we call thrust, and that's what we will be learning today. And so most of those, they are built on top of the CUDA runtime, and so the core set of APIs for managing and communicating with the GPU. And so since this course is not domain specific, so it's not about deep learning or linear algebra, we'll focus just on thrust. And so thrust will allow us to communicate with the CUDA runtime without having to reprogram everything from scratch. And so thrust is a library that helps you write a GPU accelerated program using tools that are very familiar to the C++ STL. So you have many pre-built things. So you have containers, you have algorithm, and so overall, this allows you to program on the GPU in a way more efficient and easy manner than if you had to rewrite everything from scratch. So we'll not go right now into the details of all the things you can do and use in thrust, but the whole goal of this today's DLI is to go and move forward and learn one of them at a time and discover all the things that thrust can help you with. So now let's look at how the code that we had earlier, this temperature code that was running on the CPU, how we will port it on the GPU. So you can see the first thing we changed was the container. So we changed this std vector to instead be a universal vector, because a std vector is on the CPU, but we don't want the data to be on the CPU. We want the data to be on the GPU. That's why we used here a universal vector. We'll detail more why do we say universal. But so first, universal vector will allow us to have the data on the GPU. Then, instead of just having a regular lambda, you see we added this host and device keywords. And so those will help us identify if the function can be run on the CPU or on the GPU, or both. And finally, instead of calling STT transform, we just call thrust transform. Thrust transform will do the exact same thing and you add the exact same API as STT transform, but it can use data which is on the GPU, which is here our temporary vector, which is now on the GPU. And now we just need to specify to thrust that it needs to run on the device, so on the GPU, using this thrust device. So now let's take a deeper look. So we had this lambda, right, at the top, where we did the with the computation. And if you were on the CPU, the host compiler will translate that again to a VFMA instruction that can be executed on the GPU, the CPU, sorry. But so that's where execution space comes in. We don't want the code to be executed on the CPU. We want it to be executed on the GPU. But so as we said, if we want code to be executed on the GPU, we need the compiler to emit instruction that can be executed on the GPU. So we need to tell in the code, hey, compiler, this code will be executed on the GPU, so please generate GPU instruction, because by default, it will not generate instructions for the GPU. So what we do here on the right is we added this device to the lambda, and that will tell NVCC, so the CUDA compiler, hey, NVCC, this code will be executed on the GPU, so please generate the corresponding instruction, which is in our case, again, fma.rn.f32. And this instruction can be executed on the GPU, but because we added the device, it can no longer be executed on the CPU. We told the compiler, hey, this thing will just be executed on the GPU. So it will not generate instruction for the CPU, just for the GPU. If we want the code to be executable from both the CPU side and the GPU side, we'll have to add both host and device. And so this will tell the compiler, hey, compiler, NVCC, please generate the assembly code for both the CPU and the GPU. This way, my code can work both on the CPU and on the GPU. So I can keep the same thrust transform code, but make it run either on the CPU or on the GPU based on what I need. So beside the execution space, so specifying that the code needs to be compiled on the CPU or and the GPU, there is another change. In the original code, we were using STT transform, but now we use thrust transform. So yes, there is a difference in namespace, but the main thing is we added this thrust device that you can see on the right. This is what we call an execution policy. So this will tell thrust where the algorithm should be ran. So if you say thrust host, thrust will run on the host just like STT transform would. So your code will just run in the exact same way as if you had just kept STT transform. Thrust will just make the code run on the CPU using STT transform. But on the other hand, if you say thrust device, then the algorithm will run on the GPU in the same way that it runs the CPU, in the sense that it will transform the input using the function you gave, but it will run the instruction on the GPU. And so thanks to this consistent interface, which can work in both CPU and GPU, you can easily switch between both to do testing or do benchmark. And so you don't need to maintain two separate code bases. You can just have the same thing for both CPU and the GPU. And what you just switch is the execution policy. So you go from thrust host to thrust device based on if you want the CPU or the GPU. And you might think, oh, okay, what's this execution policy thing about? But actually, it's been there for quite some time. So execution policy has been a part of C++ in C++ 17. And so in both Rust and C++ 17s, you have those execution policies which tells the function how it should be run. And so in the C++ landscape, you could pass, for example, an std execution par to parallelize automatically your algorithm on the CPU. But by default, it would just run in a single thread on the CPU. That's the same for thrust with thrust device. You're just saying thrust, hey, this algorithm, this OP thing, can you actually run it on the GPU? So you're just specifying where the computation should happen, either on the CPU or on the GPU. So it's important to understand the difference between the execution specifier and the execution policy. So when you mark a function with host or device, you're telling the compiler what it should generate as a final executable code for the machine. Should it just compile and generate code for the host, so for the CPU, or for the GPU, or for both, if you specify both host and device? This will not mean that your function will eventually be launched on the GPU. This just says to the compiler, please generate code for the CPU or the GPU or both. That's it. If you want then your code to be executed either on the CPU or on the GPU, that's where the execution policy comes in. So when you invoke this thrust transform function, you have to pass this thrust device thing to tell thrust launch your computation on the GPU. But in the same way, passing thrust host or thrust device to thrust will not generate CPU or GPU code. To do that, you need to first specify host or device. That's why you need both things. You first need to tell the compiler it needs to generate the correct assembly code by specifying host or device, and then you need to use the execution policy to tell thrust where the code should be run. If you don't do that, you will get an error. So in summary, we first have the execution space specifier, so like host and device, that we should specify, like you see on the top right in the lambda, and that will make the compiler generate the correct assembly code so that the code can be executed either on the host or the device. So all of this is at compile time. And then at runtime, to thrust transform, you need to pass an execution policy to tell thrust transform if the passed lambda should be executed on the host or on the device. And so if you want to be able to execute on either of the two at any point, you need to put both host and device so that you have the correct assembly in the end. So here you have a summary of what you can do. So if you have put host and you call thrust host, it will run on the CPU. If you have put device and you use thrust device, it will run on the GPU. But if you do only host and run on device, or only device and run on host, you will get an error. But if you put both host and device, then the code can be run on either the CPU or the GPU directly. So enough talking. Now it's your turn to do some work. So if you go in the DLI folder, you will have your first exercise, which is this 122 exercise annotate execution space, where you will have to replace all the interrogation mark to know if you're actually currently running on the CPU or on the GPU. So if you believe that the code where am I is going to be run on the CPU, you replace it with CPU. Else, if you think it's on the GPU, you will replace that with GPU. And so for this exercise, you will have 5 minutes. And so to find the exercise, just open the DLI, go into the execution spaces folder. Then inside, you have this 22 exercise annotate execution space exercise. And then once you have modified the code, you can run the cell on top to save the changes and run. Finally, once the code has been saved, following your modification to put either CPU or GPU, you can run the cell below, again using the send button. This will make your code run, compile and run, and this way you can see if the code was indeed run on the CPU or on the GPU and see if you were right. So time's up. Now let's see the solution. So as we said, the program, the CUDA program is just like at its foundation is just like any CPU program. So it's done on the CPU, just like any C++ program. So the first one, first where am I, is on the CPU. Then we called thrust for each, and we have passed thrust device. And we have correctly passed host and device as specifiers. So we know that this code will be correctly executed on the GPU. Then we call thrust for each, but this time using the execution policy thrust host. So this code will be executed on the CPU. Finally, this last line, again, since there is no specifier whatsoever, it's just like any C++ program, and so it will be executed on the CPU. So now let's move to the next exercise. So you will have to go to exercise 1.2.3, which is changing the execution space. And so the goal of this exercise is to modify this thrust for each to make it run not on the CPU, but on the GPU. And so this time again, you will have 5 minutes to complete the exercise. Time's up. So to make this algorithm work on the GPU, the only thing you need to do is to modify again the execution specifier. So here you just need to switch from thrust host to thrust device to ask thrust to run on the device. But you also need to not forget to specify how the compiler should compile a lambda, and so specify device if you want your compiler to generate code for the device. That's why you should add device at the end and not let host. You could also have put both host and device, but if you want the code for each to be run on the device by passing the thrust device, you also need to pass the device specifier. So now let's focus on a different kind of problem. Let's look at medians. So suppose we want to track the median temperature in our simulation. So one way to compute the median easily is to sort the input, as you can see here, and take the middle element. And so for now, we only cover the case where it's the amount of element it's odd. So you can just take the middle one. And so to implement that in C++, it would be fairly easy, right? You just take as input your container, then you call the std sort that will be run on the CPU, and then you just return the middle element. So you take the size divided by 2, and that's how you can get the median fairly quickly and easily. So your next exercise will be to port this median algorithm on the GPU again, using thrust and the rest specifier. And so to do that, you can go to the exercise 1.2.4, which is the compute median exercise. And for this, again, you will have 5 minutes. Okay, so thumbs up. So before showing the correct solution, let's highlight a common mistake, trying to make the median function with device. So because std sort is not annotated as a device function, this approach won't compile. But even if it did, median is called from the CPU in main, and you can't call a device function directly from the host code. You have to use, so that's why you need parallel algorithm. That's why we need thrust. Besides that, std sort is a serial algorithm by default. It will run sequentially, not in a parallel manner. So it won't be able to leverage the massive parallel power of GPUs. That's why, again, we need those parallel algorithms. That's why here, instead of using std sort, which will run sequentially on the CPU, we need instead to use thrust sort. So again, most of the algorithm you have in the STL, they are also in thrust, and that's how we can leverage easily the GPU. So here, all you need to do is call the thrust version of the algorithm, which is here thrust sort, and pass the correct specifier, which is here thrust device, in order to make the code work on the GPU. And that's it. As long as your container, so your data, is the vector, is on the GPU, and you're calling thrust instead of std, and pass the correct specifier, so thrust device, your code will run automatically on the GPU. So now let's look at another kind of problem or algorithm we could be doing on the GPU. Because some things are not as easy as just sorting. Some things require a bit more advanced algorithm. So here, let's say we want to compute the maximum difference between the old and the new temperature. So for example, let's say the first object cooled down from 42 to 31, which is a 11-degree difference. But the last one here, you can see that it cooled down from 50 all the way down to 35, which is 15-degree difference. So we don't have a thrust minimum temperature algorithm, right? That's too specific. That's okay. You can compose algorithm in order to achieve the same results. Again, doing so on the GPU. So to do so, we'll start by creating our, as always, universal vector of differences. And so that's what will store the output. So the difference between the two vectors, because we want to find the difference between the one step and another step. And so then we will use thrust transform, which, just like std transform, can take as parameter two input ranges. So here we can see that we first pass a.begin a.n, which is our first step of temperature, and then we pass b.begin, which is the second step of temperature. And then as an output, we give this vector. And finally, we have our lambda. And our lambda, again, we put hosted device so that it can be executed on either the host or the device. As input, again, we have two things, previous step and next step, or previous step and current step. And what we just want to compute is the absolute difference between the previous and the current. So we just do x minus y. And so once we have computed this difference, which will give us as an output this 11, 2, and 15, which is just, again, the difference of the two vectors together. So once we have this result, which is stored in our output vector, then we can just compute the maximum. And so to compute the maximum, what we can use is reduce. So reduce is, again, an algorithm that you can find in the STL. So you have std reduce. Std reduce simply applies a binary operator to an input container, and it reduces it, as the name stands, from n elements to just one element. And for example, you can take the sum, you can take the min, you can take the max. And so here we're taking as input our array of differences, and we just compute the max. So we reduce it from element to one element by every time just taking the max between the element. And so here the max of 11, 2, and 15 is 15. So this code will work, it will produce the correct result, but is this code efficient? So to answer this question, let's recap the key steps of this algorithm. So first, we have an allocation, which is already suboptimal because we are allocating a new array. Then we call transform, which transform two input array into one by doing the differences. So if we want to build an intuition of this step, we can consider, as we can see here on the slides, that this first difference is doing a for loop behind the scene, right? If you call std transform, it's again by default we run it sequentially, just basically do a for loop. So inside this for loop, what do? We read the first element, so a, we read the second element, so b, and finally we write the difference in the resulting vector. So we have a first read, a second read, and then finally another write. Then, once we have this difference vector, we then do the reduction. Again, std reduce, if you run it sequentially on the CPU, behind the scene is just, again, another for loop. So you're just going to read and then compute your reduction, which is here doing through a max. And so here again, you're doing every time one read. So overall, we're doing 2n reads and 1n writes for the transform step. And then in the reduction step, we do n reads. That's a lot of reads for something that looks fairly simple. So in this example, in the end, we have 3n reads because we read from 0 to n 2 times in the transform and 1 time in the reduce, and we have 1 write in the transform. The question is, if you could write the for loop yourself, couldn't you make it more efficient? Yes, you could. So if you were writing the for loop yourself, what you would be doing is this, what you can see at the bottom of the screen. So you would be declaring a max, like a local max variable that will store the maximum, then do a single for loop, not two, just a single for loop, do again the 2 reads, and then directly compute the difference and the max directly. And so this allows you to go from 3 reads and 1 writes to 2 reads and 1 writes. So that's 2 times less memory accesses, which is way better. You're doing twice less work, right? So the question is, how can we tell Thrust to do this instead of doing first transform and then reduce? So we can see our loop on the bottom. Reduce, it goes from 0 to n, and it reads the first 2 elements. So it already kind of looks like what we want to do in transform, but we want to do the reduce at the same time. So how can we try and combine those two together? Before explaining, we need to explain a tiny bit of things. So let's first talk about pointers so that we can better understand iterators. So on the slide, you can see a simple program that creates an array with 3 elements. And then we initialize a pointer with the address to the first element. And so then once we do that, we can just use this pointer with the brackets to find what's the first element, element 0, then element 1, etc. So we could say that this pointer is an iterator to this input array. So a very simple mental model for pointer is that they store a physical memory address. But so beside of that, pointers, they provide an array style interface to access the data. So if I put the 2 braces with the specific index, I will access the array at the specific address. So here, if I put 0, I will address the data at address 0, and if I put 1, at data 1. And so it's following what's the type underneath to indeed get the first integer or the second integer. And so this subscript operator, it's not limited to just pointers and array. If you think about thrust vector or std vector, you can use the same brackets. But so why does that work? That's because in C++, we can define a subscript operator just like any other function. So we can do this for any other operation on which we can do increment, decrement, additions, anything. So in other words, you can write vector at index 42, where 42 is the path to the parameter with the braces, and you can have that inside your own function. And so this allows you to define the operator in any way you want. So you can see here at the bottom, we have defined a operator braces that takes in the parameter I, which is our index here, and use it to compute what's the ith element. So to do that, we just do data plus I. So we offset the pointer by I, and then we dereference the pointer to get the correct integer. And so you can do that to any of your structure. You can define those operators. And so since we can define this operator for a class in any way, we don't have to limit ourselves to the concept of physical memory or to pointers or all of that. You can imagine a type whose subscript operator just return whatever index you pass in. For example, if I pass 42, it will return 42. And if I pass 0, it will return 0. So you can do anything you want with those iterators, right? You just override this braces operator, and you can do anything. And this will allow us to do some useful modification to our algorithm. So let's compare the pointer-based approach on the left with the custom type on the right. So when we pass in an index of 0, both print 0. When we pass an index of 1, both print 1. So both do the same. They produce the same result. So functionally, there is no difference. But because the pointer is tied to an actual physical memory address, every time you call the braces, you will do one memory reads, because behind the scene, it will have to read the underlying vector and read the memory location and return the result. And so if you read n times the vector, it will result in n memory accesses. But on the right, because we aren't really reading anything, we're just returning what's given to us as an input, we're not actually performing any memory reads. So it's far less costly to do that. So if you need to use an iterator that returns what's the current ID, you will preferably use a custom iterator, which just return the ID, then creating a custom vector, which goes from 0 to n, and then go and address this vector, because this will produce way more memory reads than the other one. So you can think of iterators as a generalization of pointer. So they provide the same interface. The iterators, they provide the same interface as the pointer, which is, you can call it with the braces, but they're not limited to going to an actual physical address. You can make it do anything you want. So the one we just talked about, which is take take an ID as input and return this same ID is what we call a counting iterator. And it allows us to represent an infinitely large amount of numbers. We could call this iterator with 0 all the way up to billions. But while doing so, we don't actually require any memory to be stored anywhere. And we don't also do any actual memory accesses when we access it, which is very powerful. But so if you want to picture yourself how a counting operator is programmed, it's just as easy as what you can see on the top right. The mental model is just this. You take I as an input and you just return I. So the counting iterator, we just saw, doesn't make any memory accesses, but not every iterator works that way. For example, let's imagine what we could call a transform iterator that references an underlying pointer. So every time we call the braces operator, instead of just returning the element like you would if you just had a regular pointer or a vector, instead what we'll do is we'll take the input and we'll multiply it by 2 and return that result. So that's what you can see on the top right. And you can see on the bottom right, for at an input, if we have 0 and 1, if we address the first one, we'll get 0 because 0 times 2 is still 0. But if we address the first element, element 1, which is equal to 1, because we return the element times 2, we now get 2. So from the outside, it looks like the entire sequence was scaled if we use this iterator. But in the end, you didn't modify the actual array. What you just did was to have a view of it where everything is scaled by 2. That's what an iterator is about. You're not actually storing anything anywhere. You're just computing it on the fly when you're asking for it. You don't need to actually store anything anywhere. Another iterator we could think of is what we call the zip iterator. So the zip iterator, just like a zip, allows you to reference 2 sequences at once. So when you ask for it, instead of returning 1 element, it will return 2 things. So you can see at the top left, you have 2 arrays, A and B. And what we want is when we ask for the first element, it will not return A nor B, but it will return both A and B. And so to do so, you can see at the bottom, we have the 2 arrays, A and B. We declare the zip iterator that takes as input A and B. And if we want to get the first element of the zip iterator, we just call obviously the braces with 0. But then out of these 2 elements, if we want to get the first one, we call stdget0. And if we want to get the second one, we call stdget1. And a potential implementation could be just what you see on the top right. You just take as a parameter the 2 pointers. And then if you're given an ID by the operator, you just return a tuple with those elements. And so that could be an implementation for the zip iterator. And this one does 2 reads, because every time you want to access 1 element, you're actually reading 2 elements, here A of I and B of I. The real power of iterator shows when you start to combine them. So let's imagine a transform iterator that also uses a zip iterator each time. So this time, if you look at the top left, we have those 2 vectors, A and B. And first thing we want to do is dip them together, because we don't want to just view A or just B. We want to view both A and B together. So that's why we did the zip. But then what we actually want is not just to get A and B. What we want is the difference between A and B. That's why once we have access to this tuple, which contains both the first element of A and the first element of B, we then compute the absolute difference of it, which returns 5. You have an example on the right, where we define a transform iterator that takes as input an index I. Then it accesses our zip iterator to get not just 1, but the 2 elements, A and B, and return the absolute difference between A and B. And so you have the example of code on the bottom right. You declare A and B. You first declare your zip iterator that takes into parameter both A and B, and you give the zip iterator to your transform iterator. So you just composed 2 iterators together, and this way, when you call for iterator 0, what you get is the output of the zip plus the transform. And so in that case, again, you just did 2n reads if you are going through the entire array, because every time what you just do is read A and B, and that's it. You're not writing the data anywhere, and you're not doing any additional reads than the two that are done through the zip iterator that is being called by this transform iterator. And that's exactly the kind of thing we'll do to do our temperature simulation. So in reality, production-grade iterators implementation are much more complex than the simple code example we have seen. But luckily, you don't have to build them yourself. We have already done that in NVIDIA. And so Thrust already provides a very wide variety of ready-to-use iterators. So you have obviously the counting iterator we talked about. We have the zip iterator. We have the transform iterator. And we call those fancy iterator. And so here you have two examples. So the first one, that's if you want to do a transform iterator. So if you recall, a transform iterator is I'm taking your input and I'm applying a transformation to it, just like a STD transform. But this time, the transformation will happen on the fly when I'm calling with the braces. So here, I take the input and I multiply it by 2. So I scale everything by 2 whenever I'm calling the thing. But I'm not, again, storing anything in memory. I'm just applying the operation on the fly. Same on the right, you have, if you want to zip, so if you want to, you have two sequences, A and B, and you want to see them as a single thing, what you will use is the zip iterator. You can just call thrust make zip iterator, takes as the parameter A and B. And this way, when you use the braces with this iterator, you will get not only A, not only B, but both A and B. And finally, you have the counting iterator, which just returns the same value as the input, which is done through make counting iterator. So thrust make counting iterator takes an integer that tells it where to start counting. So maybe we want to start counting from 1, from 5, from 0. And so, for example, in the code on the slide, we pass it onto thrust for each to print the first 42 elements. So if we pass this counting iterator to thrust for each and we tell it to execute on the device, and we pass in a lambda that prints, it will print 1, 2, 3, all the way up to 42. That's because our iterator, our counting iterator starts from 1. That's why the first one printed is 1. And it goes all the way up to 42 because the end is just begin plus 42. And you really need to understand that here, we didn't do any reads and we didn't store any memory anywhere. On the fly, when thrust for each was going through this iterator, it just called the iterator, not knowing exactly if it's a vector, if it's something else, it doesn't really care. It just called the braces operator, which in this case will return what the counting iterator is returning, which is our case, just the input index. That's why here it's just returning 1, 2, 3, 4, 5 all the way up to 42. But it's not computing anything, it's not doing any memory reads or writes, it's not storing anything anywhere. It's just on the fly returning the correct thing. So thrust make transform iterator takes two things. An iterator pointing to the underlying data, which could be here our input vector, and then a transformation function that does something to each element. So for example, here in the slide, we have a trace vector that contains a sequence with 1, 2, 3, and so on. So what we need to pass to thrust make transform iterator is the beginning of this vector. And then we need to pass the lambda. So this lambda here, what we wanted to do is to take the input value and multiply it by 2. Again, we shouldn't forget to pass both host and device because we want the code to be executable on both the CPU and the GPU. And so that will produce what we can see on the right. Whenever we want to access to the sequence, instead of just returning what's at this position in the sequence, it will return what's at this position in the sequence times 2, because that's what we passed in the transform iterator. So this time, if we call thrust for each, and we pass in this custom transform iterator we just made, instead of printing 1, 2, 3, 4, 5, etc., it will print 2, 4, 6, 8, etc., because every time it takes the input, it multiplies by 2. Again, those value those 2, 4, 6, 8, etc., they're not stored anywhere. We didn't have to create some kind of temporary vector to store those values somewhere. We didn't first took the input array, then doubled everything, stored that in another array, and then finally printed this whole array, which would have resulted in multiple reads, writes, and the creation of a new array. Here, on the fly, while we go through the vector using threads for each on the GPU using the device, we see the sequence as everything scaled up by 2. So we don't need to store anything. So now let's take a look at an example using the zip iterator. So here we have 2 vectors, A and B, with 0, 1, 2, and 5, 4, 2. So we first declare a zip iterator. Again, the zip iterator just need to take what's the beginning of both sequence, and that gives us a resulting iterator. And again, we can call our for each to call it on the device, on the GPU. And again, it will print. This time, what the for each sees is a sequence, so it will just call the braces operator. And this time, what it will do is it will print 2 numbers. That's because here, because we are using a zip iterator, the zip iterator for each index it takes as an input will generate as an output 2 values, the 2 values of the sequence, of the 2 sequence it was given as a parameter. Again, here, we're not creating any additional array anywhere. We're not doing any writes to memory. We're just on the fly, while going through this zip iterator, we are actually going through A and B at the same time and printing both at the same time. So now let's compose things together. So first, what we want to do, because we want to go through A and B at the same time to compute the maximum difference of the 2 vector, we first need a zip iterator. So the zip iterator, again, allows us to see A and B as a single thing. Then we're going to pass this zip iterator to make transform iterator. So remember, make transform iterator takes as a parameter first an iterator, which it will use to know where it should find the data it needs to work on. And then what lambda it needs to execute on this iterator. And in our case, what we want to do is take as an input the tuple for the 2 values and compute the absolute difference between element 0 and element 1. So that's why we use threads get 0 and threads get 1, and we just take the difference. So that would result in what we see below. In a single iterator, which is this resulting transform iterator, we take both A and B that we see as a single thing, and we directly on the fly apply the absolute difference, and we return that. So every time we call transform iterator with the I parameter, under the hood, all of this is going to be executed. So by just calling transform iter with the braces and I, under the hood, you're actually getting A, the first element of A, the first element of B, computing the absolute difference and returning it, all of that in a single iterator. That's why we call those fancy iterator, because they can do all sort of very fancy things. So here, this is the iterator that will help us to achieve the goal we want. So remember, we had this naive solution where we would first do the transformation, then the reduce. This meant 3 memory reads and 1 write, because we had this temporary array where we would have to store the difference before doing the reduction to find the maximum. But we saw that we could just do a single reduce operation if we had access, if we could program it ourselves, the for loop. If we could on the fly retrieve the 2 elements, compute the absolute difference and compute the max on the fly, we could achieve just 2 n reads and just 1 write. And we could achieve this, right, if we had the correct iterators. And so let's say we had such a thing, right? Let's say we had such fancy iterators to go down from 3n reads and 1 n writes to 2n reads and 1 writes. How would that impact memory? How would that impact performance, considering we have twice less memory traffic than usual, because we went down from 3 reads and 1 write to 2 reads, 2n reads and 1 write. This is how. So on the slide, we have the normalized elapsed time for different vector sizes. So remember that lower is better. We the lower we are, the faster we are. So when we're using fancy iterators, so fancy is in green compared to materialize, which is just doing the transform and the reduce, depending on the size of the array, we can go way faster. So usually it's 2x, but the speed up could climb way more. So you can see that the more elements we have, usually the faster we go. And again, because not only we do less reads and writes, we go faster, also because we don't have a temporary array anymore, the version with Iterator needs 30% less memory. So performance is not the only benefit. So when you're working with GPUs that have a limited amount of memory, let's say 8 gigabytes, not only is your code is going to go faster, but also you need less temporary memory, which means you're saving memory for the GPU. So most of the parallel algorithms we've seen so far they are very challenging to implement efficiently. That's why it's crucial for you to understand how to adopt these accelerated libraries, just like Thrust, for your unique use cases without having to re-implement all of them. So let's pause and verify your understanding of how to extend parallel algorithm to your unique use cases. This time, you want to calculate the variance of a temperature dataset, which requires us to compute the square difference of each element from the mean. So obviously, the naive approach would be to create a whole new buffer in memory to store the square differences, which again wastes both time and space. Instead of doing that, you already know that you can build fancy iterator that will compute the square difference on the fly and feed those differences straight into the reduction without either creating a separate array. So in the code snippet, you'll see a placeholder for square differences. And so your task is to replace that placeholder with a transform iterator that when dereference, so when you dereference this fancy transform iterator, it returns the square difference of the incoming value with the min. And so for this exercise, you will have 10 minutes. And you can, again, find this exercise under section 1.3. Okay, so time's up. So as we said, we want to use the fancy iterator. So what we want to do here is use a transform iterator that takes in as a parameter each time the value, because we want to compute the variance. So we need the input value minus the average, so the mean. And we take the mean as a parameter to our lambda. We don't forget to pass host and device, because we want the functor to be executable on either the CPU or the GPU. And then we can just call thrust reduce that takes as a parameter this transform iterator, which will go from 0 all the way up to the n size. So what this thrust reduce will see every time is going to try to reduce the elements of the array is not the input array, so x, but every time it will see x minus the min times x minus the min again, so power of 2. And that's how, with a single thrust reduce, we are able to do the variance instead of having to first compute value minus mean times value minus mean in a separate array, and then read it again to write the result. And because we did it this way, using fancy iterator, we just have n reads and 1 writes. We have n reads because we just ran through the x array only once, because reduce goes along the whole array. And each time on the fly, we computed the minus mean times value minus mean. And only at the very end, once we have computed all those values on the fly, we have reduced it. And this gives us a result. And we just have to do a single write to write the result. That's why we have a single write and n reads here. So now let's look at another problem. So far, we've looked at simple temperature simulations where each cell or object evolves on its own, independent of the others. And of course, that's not very realistic. So now that we're comfortable with fancy iterators, parallel algorithm, and execution spaces, let's tackle a slightly more complex scenario, the 2D heat equation. So on the screen, you can see the computational stencil that we'll use. So each cell's temperature in the next time step depends not only on its current temperature, but also on its 4 neighborhood. So the left one, the top one, the right one, and the bottom one. So in total 5, because you have also yourself, as you can see on the screen. So in the code, the 2D heat equation might look something like this. So don't worry about the specific math or constant thing, just focus on the data access pattern. You can see we're accessing the left one, the top one, the right one, the bottom one, and ourselves, and computing the result for the next iteration. And we directly see that this is pretty complicated to access. So first, we have to read the temperature of the left and right neighborhood of a given cell. So a 2D array is typically laid out in a row major order, meaning each row is placed sequentially in memory. To find a flattened 1D index of a 2D row column index, you will need to multiply row index by the width of our grid and then add the column index. So here, that's why we do row times width to jump to the start of the correct row. And then once we are at the beginning of the correct row, we can use the column to offset to the correct location. And so using the same pattern, we can take the left neighbor of a given cell, and we just subtract 1 from the column index. So the +1 is to get the right index, and the right neighbor, and the -1 is to get the left one. And so we need to write all of this to access the left and the right neighbor. And so similarly, if we want to compute the top and the bottom, we'll need to take the row -1 and the row +1 to take the top one and the bottom one. And so besides that, we also need to access the current one, our current temperature. That's what we see here. And so this code will work fine in most of the cases, but there is one issue. In reality, our grid is not infinite. We have edges. And so we need to handle those edges. And so if we try to compute the left neighbor for the leftmost cell, so we're on the leftmost possible cell, we'll go out of bound, right? So to prevent that, we need to handle boundaries condition. So in this course, we're using constant boundary condition. This means we don't update the temperature for boundary cell. They keep their original value. So if you're on the edge, you will keep your original value. That's why the code has an if statement checking whether the row and columns are strictly inside the grid. If a cell is on the edge, we skip the update and return the current cell. So that's what you can see here. If we are on the leftmost side, rightmost side, topmost side, or bottommost side, we don't do anything, we just return the value. But if we're inside, that's when we compute the stencil. So we take the arrow current value, left, right, top, bottom, and do the computation. So the next question is how we actually launch this computation on our 2D data. If you think about it, each cell in our grid corresponds to a single linear ID in a flattened, so one-dimensional space. So we can use a thrust make counting iterator to generate all possible cell ID, one from each cell, and then transform those ID into updated temperature values. But we still need to figure out which row and column this flat ID correspond to. So when we'll be using our counting iterator, it will go from 0 to n. So it will just return 1, 2, 3, 4, 5, etc. But what we want is not 0, 1, 2, 3. What we want is a position in a 2D grid. That's where the modulo and the division comes in. By dividing the cell index by the modulo of the matrix width, we get the column index. And by dividing the cell index by the matrix width, that's how we get the row index. With this, we map each flat index, so each one value from the counting iterator, to its correct 2D position. So after that, the rest of the code is the same with the boundary check logic that we used before. So essentially, we're just transforming cell ID into the next step temperature without needing an explicit loop over rows or columns. So that's what you can see on the screen. So we take a counting iterator that starts from 0. Then we call our thread transform because we want to apply a transformation to our input array. But what we wanted to do is to go from 0 all the way to n. That's why we use our counting iterator. The output will be our output vector. And so as an input parameter, we take our input pointer, the height and the width. And so every time we'll get an ID going from 0 to n, we convert the single flattened cell ID into a 2D coordinate using the modulo and the divide to get the column and the row. And then we just, if we're in the bound, we apply the stencil formula. And if we're out of the bound, so if we're on the edge, any edge, we just return the current value. And the one thing we can see here is we need to pass the input data. And we pass this data at the pointer here. And here we just don't pass in that data. What we need to do is to call thrust row pointer cast. So in standard C++, calling .data on a vector will give you the underlying row pointer. But with thrust containers, .data returns a typed iterator instead of a row pointer. So thrust need that type information for various reasons that we'll explore later. For now, the main point is that we can convert this typed iterator to a regular C++ pointer by using thrust row pointer cast. And this is how we give this row pointer to our lambda in order to then dereference this pointer to get the data that we need. So if we simulate an empty oven using this code, we can see that the entire grid is initialized with low value, and then we have a uniform temperature increase that goes from the border all the way to the middle, and you can so see that the heat is spreading from the edges all the way up to the middle. So an important thing to remember is that thrust isn't limited to algorithms that are specific to the STL, so to the C++ standard library. If there are common patterns that can be accelerated on the GPU, thrust will often provide a specialized algorithm for it. So a good example of that is thrust tabulate. So under the hood is just transforming a counting iterator, something that we've seen is quite common, those counting iterators. And so thrust gives it a dedicated name and interface. The code looks just like thrust transform, except there is no input range to pass in because the input is implicitly generated by tabulation. Instead, it just takes an output, begin, and an end iterator. Besides, being a more convenient specialized algorithm like this are often more optimized. So if you spot an algorithm whose name and purpose match what you need to do, it's often a good idea to use it. So here, instead of using transform with a counting iterator, because that's again a pattern we often see, instead we directly use tabulate. So when we use tabulate, we don't need to pass in again like a counting operator that will go from 0 to n. Automatically tabulate in this ID parameter that we get as an input, we'll get 0, 1, 2, 3, 4, 5, etc. So now we don't need to create a counting operator because tabulate will do it for us. But apart from that, the rest of the code stays exactly the same. But it just made things clearer, and we don't have to go through the step of explicitly using a counting operator with transform. Since we would just want IDs to go from 0 to n, we can just call tabulate instead. So we'll likely need to convert from a flat 1D index to a 2D coordinate in more than one place. So it's best to follow the don't repeat yourself dry principle to put that logic in a separate function. That's how row call function does. So it returns an std pair with the row and column calculated by dividing and taking a reminder against matrix widths. So that's the code you can see at the top here. For an input ID and widths, we do the division and the modulo to get the pair of the row and the column. Again, we have marked this function with host and device, that the code is generated, the assembly code is generated for both host and device. And then in our Lambda, we can use structure binding to unpack the pair directly into row and column variables. This is what we do here. We call row call, the function. And here we have this auto with the braces to directly get the row and the column out of this function. So this keeps the code cleaner and make it easier to maintain and avoid scattering the same row column formula everywhere in your code. The thing is, unfortunately, the STL, they don't know anything about CUDA, obviously. Like the STL is for the CPU and then for the GPU. So functions like std make pair, they aren't marked as host and device. So here, when we are using std make pair, this code will not be compiled properly to the device for the GPU because the std make pair function wasn't meant to work on the GPU. So what are our options here? Do we need to re-implement every single thing from the STL just to make it work on the device? So do I need to reprogram make pair? Well, no, that's a cool thing because we have libq++. So Thrust is built on top of libq++, which is a core library that provides host device friendly implementation of many C++ vocabulary type. For example, we have pairs, we have tuples, we have optionals, we have variant, we have complex, we have atomic. So not only do these types carry the proper host device annotation, but they're also optimized for the GPU specifically. That means that you can treat them as a full drop-in replacement for the usual C++ types. And they'll compile and run correctly on both CPU and GPU. So now let's see how you could swap in the code to, instead of using std pair, use the one from the libq++. So it's just as easy as that you can see on the top of the screen. Instead of using std pair, you can just call CUDA std pair. And instead of calling std make pair, you call CUDA std make pair, and that's it. Just by doing that, the code will now work both on the host and the device, so on both on the CPU and the GPU, and also it's more optimized for the GPU when it's run on the GPU, rather than something you may have programmed yourself, for example. So CUDA std pair isn't the only type that can clean up our code. Right now, you saw how we're manually converting those 2-day indices into those 1-day into 2-day indices. And it's really cumbersome. We have to do those multiplication, those plus, those minus. And it's complicated, it's hard to read, and it's error prone. So we don't want to do that, right? And so it might not be too bad when we're just flattening 2 dimension, but as soon as we go beyond that, so if we have, let's say, I don't know, a 5-dimensional array, things will go crazy, just like you can see here. And this, most likely, someone will not understand this code, someone will make a mistake, and we definitely don't want to do that, even just for 2D, but even more for more than 2D. So instead, what we would want to do is do something like on the right. So we would want to pass each index we want for each dimension and leave the implementation do the arithmetic for us. So fortunately, that's something we already have in C++. In C++, we have what we call MdSpan, which is multidimensional spans, which allows you to do just like that. Pass one parameter for each dimension you want to address. And this way, MdSpan under the hood will do those complicated computations for you and avoid that you make any mistakes. Obviously, we have introduced MdSpans from the STL, and obviously we have also that in libq++. We have CUDA std MdSpan, which is, just like for the STL, a non-owning multidimensional view that's built on top of a flat array. So here you have an example on the right where we have the data is stored at the 1D array. So we have 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5. But actually, we want to see that as a 2D array. So we want to see that as a matrix with first 0, 1, 2, then 3, 4, 5. And so MdSpan will allow us to see this 1D array as actually a 2D view, so at the matrix. And so MdSpan results in a cleaner and safer code, which in turn leads to fewer bugs. And so instead of scattering row major indices arithmetic everywhere and maybe make mistakes everywhere, you can simply provide MdSpan row and column for a 2D layout and extend the ID if you have more dimension, if you're 40, 5D, 70, 10D, how many ever you want. So that's what we'll do in our code. Instead of computing the IDs, the rows, and columns ourselves, let's just let MdSpan do the work for us. So if we just take this first example, so because MdSpan doesn't own any memory, it's just a view, you first need an underlying buffer that will hold the actual data. So we could be using a vector, but here we just decided to use a CUDA std array. And so what we want to do with this array, which goes from 0 to 5, we want to view it as a 2D matrix. So we want to act just like we were addressing it, just like a 2D matrix or an image. So that's when MdSpans come in. So they allow us to view any data as a multidimensional shape. But under the hood, it's still this 1D array. It's just a view. It's just a way of seeing the data. So to do so, we create this CUDA std MdSpan container. As a parameter, we take the pointer. So here sd.data. So we might need here the first row pointer cast. And then we take the length of each dimension. So here we want the height of the matrix, which is 2. That's why we pass 2. And then we pass 3 because we want a 2 by 3 matrix. So then we pass the width of the matrix. And just like that, now when you're addressing this MdSpan through MD, you're seeing this array, which will go from 0 to 5 as a 2D matrix just by doing so. So when you want to access this MD array, you will use parentheses. So you can see here that if you want to access the very first element, you will first pass the row index and the column index. So 0, 0 will give you the first element on the top left of the first column of the first row. What you can see on the right on the 2D view is 0. But if I want to address the second row and address the last column, so row 1, column 2, I will pass in MD1, comma 2. This will give me the number 5. So again, through this MdSpan, we can address this 1D array, but seeing it through the lens of a 2D matrix. And so this makes the code way cleaner than if we had to manually compute all the indices. And obviously, so you can query the full size of the array by calling md.size to know what's the full length. You can also query what's the length of each dimension. So here in our example, if we call md.extent of 0, we'll get the amount of rows, so here 2. And if we call md.extent 1, we'll get the size of the second dimension, which is here columns, and so we have 3 columns. So you can query elements, you can get the full size, and you can get the length of each dimension. So as you saw, we had a code which was very complicated because we were using row pointer, which we don't want to use, and we were computing indices ourselves, but we don't want to do that. We could replace all of that with MdSpans, and we know we can use MdSpans on the GPU because we have CUDA MdSpans. So your exercise, and you will have 6 minutes to do so, which is in the section 1.4.2, which is exercise MdSpan. You need to change the code in order to make it work on using MdSpans instead of using row pointers and manually computing each index each time. And so you'll get 6 minutes. Okay, time's up. So as we said, if we want to use MdSpans, we first need to create a view of the data. That's why we will first create a CUDA std MdSpan. We need to use CUDA std MdSpan and not std MdSpan because we want it to work on the GPU. Then, to create it, we need first the data location. That's why we need to use in.data and convert this data to a row pointer using thrust row pointer cast. Then we pass in the matrix height and then the matrix width. And so now our thrust tabulate doesn't take as parameter a row pointer anymore. It takes as a parameter directly the MdSpan. And so now, because we're using this MdSpan, to get the column, we can just use MdSpan.extend1 to get the width and find the column, and same for the row using divide. That's why we know if we are inside or outside, if we are on the edges or inside. And finally, the best thing is we don't need to compute all the indices ourselves. We can just see here that to get the neighbor on the left, we just pass in the current row we are on, and we want the column on our left. So we can just pass column -1. For our current one, we just passed row and column. And for the right one, we just pass row and column +1 because we just want the one on the right. Same goes for the top and the bottom. For the bottom one, we can just call run row -1 to just get the one below us. And for the top one, we can just get row +1 to get the one above us. And so we can see that this code is way easier to read, well easier to maintain, less error prone, and cleaner. The type for CUDA STD-SPAN can get pretty involved because it lets you specify static as well as dynamic extents, so for your dimension. And you can also specify a memory layout. So typically, you should define domain-specific type aliases instead of just using MdSpans directly. For example, we could define a type called temperature grid. And so this alias hides the template complexity and makes your code easier to read and maintain. It also makes it clear that this MdSpan is meant to handle a 2D grid of floats. So here you can see at the top that if you want to use an MdSpan of floats with 2 dimension, you would call it this way with the MdSpan and the std d extents for a dynamic version. And instead of having all this type stored, you will be using calling using that you can define temperature grid f to be this MdSpan array. Same if you want a version for the doubles. So this way, it will again make your code cleaner and simpler to use rather than call the whole MdSpan semantic, which can be quite verbose. So now that we have a domain-specific alias for MdSpan, we can use it in our function signature. So, for example, in the code in the slide, the compute function we have at the top, it takes in an MdSpan, but instead of taking MdSpan as a parameter, we can take a temperature grid f. This way, again, it makes the code cleaner. We know what this function does and on what kind of data it's working on, rather than just saying MdSpan and we don't necessarily know what it's used for. Okay, so at this point, our simulator is coming together nicely, but constantly writing out all the data to disk for visualization, which can be an overkill. So each time we're done with the simulation, we write to disk to be able to see it. So instead, we can track something simpler, like per row total temperature. This way, we can easily see how much heat accumulates at the boundaries over time without having to dump every cell's temperature. To visualize what I mean, imagine we take each row of our 2D grid, add up the temperature of every cell in that row, and store the sum in a 1D vector. So you can see here on the example on the slide, if we consider the temperature as a 2D matrix, on the top we have 5, 5, and 5. We can take the sum and store that as a 15. Same for the bottom, we can take all the 3's and compute the sum and store that as a 9. So now the question is, how do we implement the row-wise aggregation in obviously a clean and efficient way? So we could use first tabulate, calling again on the device to execute on the device. The output will be our sum vector. We declare our functor again with host and device so that it can be used on the CPU and the GPU. As a parameter, we'll have a row ID because we're executing over the output array, which is of size 2. And so for each row, we'll just run a for loop to go from column 0 all the way to the last column. We'll just do our for loop with doing a plus equal each time, and finally return the solution. That will work, that will produce the correct result, but is that a good solution? Let's think in terms of performance application. So when you write code this way, it's important to keep in mind that the GPU doesn't automatically parallelize the loop inside our lambda. Thrust only parallelize at the level of rows because we're calling thrust tabulate on row indices. So if you have millions of columns, but only a handful of rows, you will end up just with a few threads, each doing a massive amount of rows. This will leave the GPU severely underutilized. So here you see, if your rows, you just had 2 rows, but each row were 1 billion elements, you would just be using 2 CUDA cores, so 2 threads, and each doing 1 billion plus operation, which is severely underutilizing the vast majority of the GPU. So what we would want to use is all the CUDA cores of the GPU. So how do we fix this? How do we somewhat distribute the work across all the threads? In other words, we want each column in a row to be handled in parallel. So let's explore how we can reorganize our code to achieve just that. But just like before, we should begin by naming the operation we're trying to perform. If we ignore the fact that we have a row dimension, it basically looks like a standard reduction, right? We want to sum things together, so we want to reduce an element to just one element, here using the sum operation. Except here, we're grouping values by row. And turns out we're lucky, Thrust has an algorithm for just that, which is called reduce by key. And so unlike a plain reduce by key takes 2 input ranges, the keys and the values, and it then groups together consecutive values that share the same key and reduces each group independently. So in our case, the row index naturally become our key, and all the cells in a given row share the same ID, and we'll thus sum all the cells together. This way, we spread the work across many threads while still ending up with the final sum per row. So here you have the examples where all the first row will have the key 0, which corresponds to the row ID. Here we'll have all the keys corresponding to the second row, so they will all have the row ID 1 because they all are associated with the second row. And then we have just the value, which is just our array, seen as a one-dimensional array. And so what Thrust reduce by key will do is it will reduce all those keys together because they share, again, the same key. They are consecutively sharing the same key. So it will reduce all those values together. And then here, because the key is different, and again, they all consecutively share the same key, all the 3 elements will be reduced together. And so in the end, we will indeed get the correct result, which is 15 and 9. But this time, Thrust did the work in parallel for us of attributing a certain amount of CUDA cores to each set of keys that are to reduce. So to use reduce by key, we need each cell in the grid to know its row key. So the straightforward and naive way to set this up is to create a row ID vector. So again, we are creating a temporary vector where each value inside will be what's the row index. So to do that, we can just create, again, a universal vector that will have the size of the whole vector, so height times width, and we'll go over it and just return I divided by width. And so this way we have correctly a temporary array which has the key 0, 0, 0, 0, then 1, 1, 1, 1, 1, then 2, 2, 2, 2, 2. So it will contain the row, the correct row index for each row, and so on. But so here we had to materialize this row index and create a temporary array. And so once we have this row ID vector, we can call reduce by key. So what we need to pass is first the row IDs that begin at n, which is our input keys. And so here again, they will just contain consecutively the key for each row. So 0, 0, 0, 0 for the first row, 1, 1, 1, 1, 1 for the second row, etc. So this way, it will be able to reduce by key, so in our case, by row. Then we have the input value. Here, our temperature. That's why we pass in temp.begin as the input value. Then we have this make discard iterator. What's this? So make discard iterator is our output iterator, and we'll explain in a moment why we have this here and not just some output vector. And then finally, we have the output value, which is where we will store the final result, which is here in our sum array. And now doing this, we're sure that we are not only reducing per row, just like we did in our first version with the tabulate and the for loop, but instead, because we didn't write the for loop ourselves, which will leave the GPU underutilized, here we're leaving thrust do the work of parallelizing over each row. And by default, obviously reduce by key will write both the key and the values into the output iterator. But in our case, we already know each row corresponds to a unique key in order. So writing out those row ID would be redundant. That's why to save bandwidth, we use the make discard iterator for the key output. So a discard iterator simply ignores any value written to it. So we keep storing that integer sequence and keep only the per row sum. So here you can see how a discard iterator could be implemented. Here you see on the right, no matter what you give it as an input, it will just do nothing with it. It will just return nothing. So no matter what you give it as an input, it will just ignore it and do nothing. And in that case, that's what we want to do, because we don't care what's the result in terms of key. We just want the summary to be written. That's why here we pass in the discard iterator. This way we do less writes. So these changes translate into roughly 100-fold speedup compared to our initial approach. So writing the first tabulate with the for loop, which relied on tabulating the for loop in the lambda. So it's a striking reminder that GPU, they don't magically parallelize your code, right? You need to design your data processing so all the GPU threads, the CUDA calls, share some workload. So whenever you see a loop inside a default lambda, ask yourself if there's not a more parallel way to do it. So if there's not a way that I can use thrust to make that more parallel. So here, again, using reduce by key instead of using the thrust tabulate with the for loop, it makes things around 100x faster when we have a large enough amount of columns. So we already have eliminated most sources of inefficiencies, but it's still like we have used the discard operator to do less writes, and we're using the reduce by key. But right now, our algorithm is making two paths through memory, one for the temperature value and another for the row IDs. And we don't actually need to store those row IDs in memory at all. Think about how we generated the row IDs by transforming cell indices by dividing them by the width. So instead of storing that result in a temporary row IDs array, we could again use a fancy iterator. So to do so, we use a counting iterators for the cells. So it will just count the cell ID from 1 to all the way to the amount of cells. And on top of this counting iterator, we make it fancy by using a transform iterator that will convert every index, so every 1D index from 0 to n, into a row ID on the fly. So this way, we never have to create a temporary array, and we never have to write to the row ID out to memory. So in the next exercise, you will have to do just that. So transform the code to, instead of using a temporary array, directly do the reduce by key using a fancy iterator that will directly compute the row ID. And this way, you don't have to write to the temporary array, and you don't have to read to this temporary array, and you don't need to allocate. And so for this exercise, you'll have, okay, so time's up. So again, our goal here was to, instead of having here a temporary array here that will store the row indices. So we have to create this temporary array. We have to write into it to write the values. And then in the reduce by key, we have to read from it, which results in 2n reads, one for the heat value and one for this row array. And we have to write one to first create this row ID. So we have to write to the row ID, and finally one to write to the sum array, which is our output. Now, using fancy iterator, we are just have n reads and n writes. And we achieve this by using, again, a transform iterator on a counting iterator. So first, we want to use the counting iterator to go from 0 all the way up to n. To do so, we just create a counting iterator which starts from 0. Then we compose a transform iterator which takes as input this counting iterator. So this transform iterator will just dereference this counting iterator and get 0, 1, 2, 3, 4, 5. But what we want is not the 0, 1, 2, 3, 4, 5. What we want is the correct index, the correct row index. So to do that, we can just divide the current index, which is I, by the width. By doing so, we'll correctly get 0, 0, 0, 0, 0, 0 for the first row, then 1, 1, 1, 1, 1 for the second row, then 2, 2, 2, 2, 2 for the second row. And this way, this is far more efficient because we don't need to store the things temporarily, we don't need to write, we don't need to read. Now, reduce by key again will, on the fly, without having to do any reads, any writes, realize when it will start dereferencing the fancy transform iterator we just made, that this position is actually the row number 0, the row number 1, the row number 3. And so it will know how it should do the reduction by key, because it will on the fly know, oh, those 10 consecutive values are all coming from row 0, because those 10, when I use the iterator on the 10 first value, I got 0 each time. So all those 10 first value are from row 0, so I should reduce them together. And all of this was done on the fly again. So we didn't have to allocate anything. And so if we take a look at the results, so here is again materialize versus fancy, so using the custom iterator. So we can see here that reduce by key was already 100x faster than doing the tabulate with the for loop. But now using fancy iterator with the reduce by key is 300x faster. So by cutting out the extra memory reads from row indices, we're making much better use of the GPU high memory bandwidth, because now all the things we read from memory are strictly what we need from memory. We're not reading anything that is not useful from their memory than what's actually useful for the computation. Now that we've seen how powerful fancy iterators can be, let's explore what else we can do with them. So far, we've been transforming value as we read them from an iterator, but you can also transform value as you write them by adding another level of indirection to the output side. So in the example on the slide, we return a tiny wrapper object from the iterator subscript operator. So when we assign a value to the wrapper, we assign operator and apply a transformation. So that's what you can see on the right. So you can see here the wrapper is taking as an input a value and writing, for example, value divided by 2. So we could imagine, for example, a transform output iterator that we can see below that takes, again, as a parameter, some index, and will return this value plus the index, but we apply the wrapper over it. So if you look at the example at the bottom, from an input array 0, 1, 2, when we're writing to address 0 and address 1, so we're writing 10 and 20, because we're addressing this array through the transform output iterator, instead of writing 10 and writing 20, because it goes through our transform input iterator, we divide the value by 2. So we divide 10 by 2 and we divide 20 by 2. So instead of storing 10 and 20, we're storing 5 and 10. That's why when we print the results, we see 5 and 10. And so again, we don't have to create any temporary data, anything. Everything is done on the fly. So on the fly, while doing our writes, instead of storing the value that is given to us. We store the value divided by 2 here in our example. This, again, can be used in different algorithms. So let's do another exercise. So this exercise is exercise 1.5.3, which is the exercise segmented mean. And so here your goal is to use a transform output iterator to compute the row mean. So this transform output iterator ID is really handy for our problem. So right now, each row sum can be a very large number, which isn't always meaningful in practice. We're more interested in the average temperature per row. So of course, we could do another path to divide those sums by the row widths. But that would mean an extra reads and writes, right? So if we had to go through the sum array after having generated with our thrust divided by key to divide each row by the row width, again, we will do an extra read and we will do an extra write, and we don't want to do that. That's why we use transform output iterator. So we want to directly, on the fly, convert the total into mints by dividing it by the width of the row. So that's what you will try to do in the next 10 minutes. So time's up. Let's look at the solution. So the only thing we need to do is we need to declare a transform output iterator using make transform output iterator. This iterator will take the mean at the begin because we're gonna go along the mean vector, and as a functor we want to take the mean functor. So this functor takes as a parameter the result of the summation, so x, because we're summing on the results on the sum array, and we want to divide by the width because we don't want just the sum, we want the average. And so now when we call our reduce by key, because we're passing this means output custom output iterator, instead of writing the sum of each row, when the write will happen on the fly, it will not write the sum, it will write the sum divided by the width. So just see how many things we're doing with this reduce by key by composing all of our iterators together. And this again allows us to just have n reads and n writes while doing so many things in parallel. So up to this point, we focused on optimizing our temperature simulation by cutting out unnecessary reads and writes by using fancy iterator. And we also saw how using certain algorithm allowed us to harness the massive parallel power of the GPU, so all the CUDA cores, all the threads. So now let's take a step back and study the input-output of our current simulation. So on the slide, you can see that we initialize this prev buffer, and we also initialize a next buffer. And so we will store the data from this prev buffer into disk in a loop. And so every time we see that we do a simulation, then we do a store into the disk at each step. And so if you see the timing on the right, we can see that the first simulate is rather quick. Then we have a store. And then the next simulate, for some reason, is slow. Then we have another simulate, which is fast, and another simulate, which is fast. Then we again store to disk. It's again making the following simulate slow. And it's unclear as to why is this happening. So why, after a store to disk, is our simulation step slower than when you're just doing more simulates after a first one? So simulates usually checks just a few milliseconds, as we can see, but when it's just after a store, now it takes 100x longer. And that's weird. Why is our simulation slower when it comes after a store? So that's why we need to remember the difference between memory spaces. So remember, when we talked about the difference between a CPU and the GPU, as in a car versus a bus, so we said that GPUs, they have a much lower latency, much higher latency, but a much higher memory bandwidth. Whereas the CPU, they have a much lower latency, so they can access data way faster, but the memory bandwidth is much lower, so it can access less data per second than the GPU. And so that's why it's important to know where your data is, so to know the notion of memory spaces. So currently, we never thought, when we were doing our simulation using thrust, where is the data? So, okay, I'm asking the compiler to generate the code so that it can be executed in the GPU. And okay, I'm asking thrust to then execute the code on GPU by using device. But where is the data? So far, we never discussed where is the data. So when we switched from std vector to thrust universal vector, we just said, oh, it's going to work fine on the GPU, and it is. Using thrust universal vector allows us to have a unified memory. This way, it means that our data can be both on the CPU and the GPU and can be accessed in both cases. So under the hood, though the CPU and the GPU, they may have a separate memory space, right? The CPU has its RAM and the GPU has the VRAM. Whenever the CPU or the GPU access the data, CUDA might have to silently transfer the data from the CPU to the GPU or the other way around. Because when you're on the CPU and you want to access the data, this data might be on the GPU. And oppositely, when you're on the GPU and you want to access the data, at the current time, it might be on the CPU. You don't have to know about it. You don't, and it will all of this will be done for you. But we have to, under the hood, keep a copy of both, one for the CPU and one of the GPU. And so to do so, we need to transfer the data over from the CPU to the GPU. Thing is, this step is kind of slow. Transferring the data from the CPU to the GPU takes time, and the other way around as well. That's why this comes at a performance cost. So ideally, if we're in a program where those transfers take time, we want to care about the memory spaces and we want to know where the data is to not have to pay the cost of the transfer. Note that sometimes some applications do not suffer from those transfers, and you could keep thrust universal vector without any major performance costs. So that's what's going on when you are using a universal vector. So imagine the data is in the device memory. So currently it's in the device memory on the right? You have your vector of two elements, u vector 0, u vector 1, and you are trying to store the data on the CPU. So the CPU wants to access the data, right? But the data is not on the CPU currently, it's on the GPU. So CUDA first need to copy the data from the device to the host memory. And so this process takes time, right? It needs to copy chunks of memory from the GPU to the CPU. And so if you're accessing data contiguously, this will go fine. But if you're accessing the array in a random manner, it will potentially trigger many different copies from the GPU to the CPU to copy all those different random locations from your vector from the GPU to the CPU. So once the data from the GPU has been transferred and stored from the GPU memory all the way down to the host memory, so once the copy is done and valid, then we can do the store to the disk, right? Because to store the memory to disk, we need it to be on the CPU. But then we call simulate again. And simulate needs the data to be again on the GPU. So again, the GPU will try to access this data. It will realize that currently this data is not on the GPU, but it's on the CPU. So it will need to again do an implicit copy of the data which is on the CPU back to the GPU. That's why our first simulate after a store to disk is slow, because after a store to disk, the data is not on the GPU anymore, it's on the CPU. That's why it needs 100 more times, because it first needs to copy the data from the CPU to the GPU, which is very slow. And only then, once it's done, it can start a simulation. But then the next simulation, because the data is already on the GPU, it is faster to compute. So to solve our performance problem here, we can make the GPU and CPU transfers explicit. But first, we need to be able to create storage that lives on just one processor, so either the CPU or the GPU. That's perfect because thrust already has that. We have the thrust host vector, which is just like an std vector. It's just that we specify host because we need to specify that the data will be in the memory space of the CPU. And oppositely, we have thrust device vector, which is also constructed on the host, but this time the memory is allocated on the device. So host memory is constructed on the host and allocated on the host and accessible from the host, but not from the device. You cannot access host memory on the device, just like you cannot access an std vector from a GPU function. And in the same way, the device vector, yes, you will allocate it from the host, but the data, the actual data, will be stored on the GPU memory, and you cannot access it from the host. If you try to read a device data from the host, it will crash. But obviously, you can access it from the device, from a thrust for each, from a thrust stored that is ran on the GPU. So by choosing the right containers, we avoid the hidden back and forth cost of having, because we're using unified memory and we don't want to care about the memory spaces, we have to pay the cost of transferring back and forth at places maybe where we maybe don't want to do this transfer. While if we use explicit containers to explicitly have the data on the host or on the device, we can handle when we want to move the data from the CPU to the GPU to do so when it makes sense, when it's necessary. So we can handle the copy ourselves by simply using thrust copy. Just like we have std copy, we have thrust copy. And so under the hood, it will use the correct instruction to either copy the data from the host to the device, or the device to the host, or the host to the host, or the device to the device. So you don't actually need to know where the data currently is. You just need to go press copy, and it will do the copy for you in the fastest way possible. So now we just arrived to the final exercise of this first section. And so this time we'll move away from using those universal vectors that we've been using from the start here for the pref step and the next step. And so now instead we want to use separate memory container, one explicitly for the host and one explicitly for the device, to avoid paying the high simulate cost after the store. Because remember, after the store, the data from the universal vector is now on the CPU. And so for the next simulate, it needs to move the data from the CPU to the GPU, which is slow. So you'll have to allocate a host vector to hold the copy of data in the CPU space, and you thrust copy when it makes sense to transfer the data back between either the device or the host as needed. And so for this exercise, you will have 12 minutes starting now. Okay, so now that we're done, let's see the solution. So here we now need 3 vectors. The 2 vectors that we do the simulation on, the prev and the next, we always want it to be on the GPU because we always do the simulation on the GPU. So we always want to have the previous data on the GPU and the next data on the GPU, and we want to iterate every time 3 steps always on the GPU. The only time where we want to have the data on the CPU is when we do the store to the disk, right? So that's why we need to add this thrust copy to copy the previous data to the previous vector. So usually we add a D when the data is on the device and an H when the data is on the host. That's why here we have the dprev, dnext, and hprev. And so here at the beginning of the loop, we use thrust copy to copy the device prev all the way to H, and then we can do the store. So each time we need to store result to disk, we first explicitly copy dprev to hprev using thrust copy, and we then pass hprev to the store function, which records the data on the CPU side. So now there's no hidden transfer between the host and the device. So now dprev and dnext are always on the GPU, and we always simulate on the GPU. And so now all the transfers are explicitly done on the GPU. And now with this change, the data only crosses the CPU to GPU boundary at times when explicit shows. And this allows us, as you can see, to have our simulates only not have a performance drop right after the store. So right after the store, the simulate is still as fast as usual because the data is already on the GPU. You don't have to do some ping pong between the host and the device memory. Okay, so let's take a step back and recall everything we have seen throughout this first session. So first, we have used the NVCC compiler to compile some C++ code to the correct assembly language. So remember, the computer, it doesn't understand C++ code, right? Temp I plus k times diff means nothing to a computer. What the computer understands is assembly language. And based on which computer you're using, the assembly language will be different. So if you're using an x86 CPU, you will use G++ to compile the input C++ into assembly language that makes sense. If you're using an ARM CPU, you will use another compiler to compile to yet another assembly language that the ARM CPU can understand. And in the same manner, if you want your C++ code or your CUDA code to be executable by the GPU, you will need to use the NVCC compiler to transform your input C++ expression into the correct output assembly language that the GPU can understand. Then we have seen that usually when you want to write code for the GPU, you don't need to write everything yourself by hand. If you're targeting a specific domain, usually you already have libraries for that, right? If you're doing signal processing, you have QFFT. If you're doing sparse linear algebra, you have QSparse. If you're doing dense linear algebra, you have QBLAS. And so if you have a need that is a bit more general purpose, like you want to do just loop over data, do sorting, do reductions, we have Thrust for that, which is more general, but still will allow you to run your code on the GPU without having to rewrite everything yourself. And so when you're writing CUDA code, you need to remember the difference between execution specifiers and execution policies. So execution specifier, they will tell you for what architecture should the code be compiled. So when you declare the lambda or the function you want to be executed on the GPU, you need to specify device to tell the compiler, please generate the correct assembly code that my GPU can read with this lambda function. And if you want to have the code to be able to run on both CPU and GPU, you need to specify both host and device so that the compiler generate code, assembly code for both architecture, the host and the device architecture. Then once your function or lambda is correctly compiled, you can then use your execution policy, so your execution specifier, to say if the code that you just compiled should be run on the CPU or on the GPU. To do so, you can just use Thrust, which has most of the STL and more functions, and you can pass to Thrust if you want the function to be run on the host by using Thrust host, or on the device by using Thrust device. Another thing we have discussed is to avoid serialization as much as possible. So when you think of how your code is currently implemented, if your conclusion is that you're going to use 2, 10, 100, even 1,000 different threads in parallel, usually this is not enough at all to saturate the GPU. So you should write your algorithm by using Thrust, or even call already implemented Thrust functions like sort or reduce by key to correctly utilize your whole GPU and not reduce the parallelization potential. Finally, we have also saw that if your code is often doing back and forth between the host and the device, or between the CPU and the GPU, under the hood, the unified memory space handles that for you by doing copies, but those copies can take time. That's why in those cases, you need to use explicit memory spaces. So you need to use Thrust host vector if your data is going to be on the host, and Thrust device vector if your data is going to be on the device. And so anything you do on the host, you do it on the host, on the Thrust host vector, and anything you do on the device, you do it on the Thrust device vector. This way, all the computation you will do on the GPU will stay on the GPU, and all the computation on the host will stay on the host. And this way, you never have copies between the host and the device at places where you don't want it to happen. But in this way, in this case, you have to handle it yourself by using Thrust copy. Finally, we have seen that if a specific Thrust algorithm does not explicitly do what you want, in our case, we wanted to compute the absolute difference of two arrays, or even the max absolute difference of two arrays. Well, we don't have a thrust maximum absolute difference of two array function, but what we have is thrust reduce and fancy iterator. And so composing existing algorithm, in our case reduce, with fancy iterator, we can still achieve complicated patterns just like this one, where composing reduce or transform with zip iterator and transform iterator, we're able to achieve those complex patterns while still leveraging the GPU in the most efficient way. So you should be using fancy iterators whenever you can. And so that's the end of this section. And so we can pause and do the lunch break now. And so if, please, if you have any feedback, there is a feedback session on the DLI website where you can post any feedbacks.